Here's another loose end. When we discussed variant 5 for LU factorization, but the blocked algorithm, what we ran into was that the current block was factored, and then the matrix to the right had to be updated by A12 becomes L11 inverse times A12, and the matrix below here had to be updated with A21 becomes A21 times U11 inverse. Now, just like for the triangular solve, we said you shouldn't really invert the matrix, you should compute with it. Here too, we don't really want to compute with it like this. So, what do we have here? Well, let's abstract away from the details here. What we really have here is an operation that is Lx is equal to B, where you want to solve knowing what L is and what B is for x, and then in the end x overrides B. Alright, now if we draw a picture, we have a lower triangular matrix, actually a unit lower triangular matrix, times a block like that is equal to a block like that. Now, just like for the symmetric matrix multiply in week 5, you can partition L into quadrants and then partition X and B conformally. But you can also leave L alone and say partition only X and B into a left and a right part. Now, if you do that, then you actually end up with a set of algorithms that either march through X from left to right one column at a time, or from right to left one column at a time. Or a block if you chose to make it a blocked algorithm. It turns out that what you do with each column, let's go and have a look at the unblocked algorithm, what you do there is actually a triangular solve, because this times that column has to equal that column. That's something you learn from multiplying partition matrices together. So this particular operation, where you know L and you know B and you want to solve for X, is known as a triangular solve with multiple right-hand sides. Right-hand sides. Or short TRSM. Triangular solve with multiple right-hand sides. Okay? And, I want to stress again, it's like solving with each column of X and B separately, except you can think of it as a bigger operation, and then you have more potential for creating different algorithms. Okay, so this you really would implement as that operation, and again, you can come up with lots of different partition matrix expressions, you can come up with lots of different loop invariants, and you can come up with lots of different variants, both unblocked and blocked. This one similarly you can think of as X times U is equal to B. Okay, what did we do there? We brought this to the other side, and then we view this as B, and we view this as X, except that in the end we'll overwrite B with the result X. And now we know this, and we know that. Well, that's also a triangular solve with multiple right-hand sides. Why? Because you can always take the transpose of both of these, not explicitly, but implicitly, in the specification of the operation. This then becomes U transpose X transpose is equal to B transpose, where this is known and that is known and this is to be computed and is to override B. And then all of a sudden you recognize it as a triangular solve because U is triangular and it's just one of those special cases. So, sub-operations you encounter when implementing a blocked LU factorization are triangular solves with multiple right-hand sides. And obviously you have the case where the matrix is or is not transposed, where it's lower triangular or upper triangular, whether it appears on the right or on the left. And finally, whether it's unit triangular or not unit triangular. Lots of different options, lots of different algorithms, lots of different PMEs, lots of different loop invariants, lots of different algorithmic variants, lots of homework exercises. But hopefully you don't have to do all of those homework exercises just to kind of get the gist of what we're after here. You've seen enough.